Hello, this is Dr. Zhuyi Jackie Huang, an associate professor at Villanova University. This video is designed for the readers of my book, Doing Cool Research Projects in Simulating Biochemical Reactors on Computers by a Layperson, MATLAB, and R code and instruction videos. If you have not bought my book, please do not watch the video. And here is the link for you to buy my book. And here is the announcement of the copyright. Please keep this video to yourself. I hope this video can help you in your learning. In this video, I will show you how to solve the learning car model in R. And actually, we have solved this model in Simulink before. And after this simulation, and you will see the difference between R and Simulink. So here's the model. So here I don't go over the detail of the model. I believe you already learned that from the previous chapter. So now the job here is we're going to solve this ODE model. So x is distance, a is the acceleration, and we're going to do the simulations for two different accelerations. So this one is for Ferrari car, and this one is for the regular car, if you still remember. Again, you don't have to solve the MATLAB Simulink model before you use R to solve the model, because R and Simulink, they are totally separately. So you don't even know R, you don't have to know Simulink and before you use R, right? So they're totally different, okay? So hopefully you will find it's easier to solve the ODE in R than Simulink. Actually, Simulink is easier to learn, but R should be faster, right? Okay. Now, so we had the parameter values for the two accelerations. Okay. Now I'll show you step by step. Firstly, you're going to set up the working directory. So go to the R, and then and you could go to the files, and then you could just click this one, and then pick the folder, you're going to save the data or save the programs. So for me, I saved the program in R folder. Okay, and after you select the folder, and then you go to just click more, and then set as working directory, right? And then you see, for me, I see all the programs I have in this folder. Okay, so the first step for you to do again is set up the working directory, right? Okay, so after that, and we're going to set up create a function for the ODE model. Right, so here is the format, and you should follow and to type in your ODE model. So typically, we could see this is the function's name. So for us, we use the car to represent the function for the ODE model of the car. And then after that, you have a function here, and then you have the time, and then you have y. So in R, right, we use R, we use y instead of x. So y actually is x in R. Okay, so we have the t is the time, y is the variable. So this is the time, this is the variable, and here we only have one in the model, and then this is the parameter vector. Alright, but for us we only have one parameter, right? A is the acceleration. So we have one parameter here, so we get one here. So this is the format. So you define the name of the ODE, and then you use the keyword function here, and then you just put the time and the state variables, and then the parameter vector here. So after that, and then you're going to use the format right here. So you're going to use width. So this is width. So you place it from here to here. So this whole part, this part for width. So in width you have two parts. Right, it's the first part here, right, and then you have comma, right, and then after that you have another part, this second part here. So is the curly parenthesis. So in the first part means what? Means the width means what? Means we evaluate the ODE model. Right, actually the ODE model is presented in the curly parenthesis, right, and using the value of y and the parameter, parameter vectors, right. So with list means we as list means we use those parameters or value, and to evaluate this whole part is ODE model, right? So ODE model, right? Okay. So this whole part is ODE model, right? So you can see here. So in the core model, so you got as dot list. Like this function, hey, means that hey, we're going to use this variable and parameters, and to evaluate this ODE model, right? So when we evaluate remember we had the ds dt equal to a times t. But again, we don't use x, so we use dy dt in R, and then we also have a times t, right? Okay, so therefore, so when we set up the ODE model, firstly you're going to set up the parameter, right? Especially here is the a equal to the first element of the parameter vector, right? And then after that we had dy is the derivative of y over t. So we don't have dy dt, we just put dy to represent dy dt. Okay, so we have dy equal to a times t. Okay, so this is the derivative. So after that we need to tell all which term represents the derivative. So we say list, right? We use the dy as the derivative term, right, to return the value of derivative, so that the R program can calculate the derivative and then use that and to determine the value of the variable or the output in the next time step, right? So again, I don't talk about how to solve the ODE in this video. Alright, please check chapter 2 for the detail about the introduction of how to solve ODE. Okay, so in R you just use this format, right? Okay, so determine the name of the ODE, and then right and use this format. And then what you really need to do is actually is this part, right? How to set up the ODE model, okay, and also determine the name, right? So these are the two things actually you need to take care of when you develop model. All right. Okay. Now so now let's type in the ODE model first, and then after that we could set up the initial, very similar to how we solve the ODE model in MATLAB. You're going to set up the initial values for the model variables, and then you set up the values of the parameters, and then you also select actually also install the ODE solver, and then to solve the to solve the problem. All right. Okay. So before that, before I show you how to solve the ODE, I would type in the ODE model first. So you could type in ODE model and in a new script. So you could just click this one, right? Click new. So R script, right? Okay. So therefore you get here, for example, I get this new script document. So then I would type in. So I would type in the model is car. All right, and then this arrow here, this means equal, right? Okay, and then I put function, and then we have t, y, right, the parameters, okay. And after that, I had the correct parentheses. So before I continue, I will save it as, for example, main car. Okay. So and then after that, I will type in width, right? Width you have parentheses, okay. Again, width you have two parts, right? The first one is you're gonna tell the R that we're gonna have use, right, the Y as the state variable, and then the palms as the parameter vector, right, and this comma to evaluate the ODE model. The ODE model you're gonna type in here. Okay. So I'm going to delete this line here. So you can see the good thing for the R is you just type in the model directly. So I would say, how can we determine the parameter value of A? A actually is the acceleration, right? So the parameter value for this, and actually is the first element in the parameter vector. Again, you don't have to put the semicolon here. It doesn't change the result. So in all the semicolons, it doesn't change the program, right? But in MATLAB, if you don't want to show the value of that variable, you just put semicolon. Right? If you want to show it, and then you just remove the semicolon. But in R, there's no difference. And then I will type in the derivative is dy dt. Actually, I just put dy here, and then equal a. So we already determined a, right? So we get the a value from the parameter vector. So after we get it, and then we just times t. Okay. So we get the ODE model already. And then after that, and then I will tell the program, we have to tell the program which term is for the derivative, right? So you get list, and here c dy, right? So this is a vector, right? C is a defined vector, the derivative, right? And then the derivative is dy. Okay, so we just save it. So we had the ODE model already, right? I think it's pretty straightforward, right, for you to type in ODE model. Now we need to solve the ODE model. So before that, we had to install the ODE server, right? DESolve. Okay, and just like MATLAB, right? and we're going to use the OD server from R. Okay, but in R there's a lot of option for you to pick the OD server, right? Okay, so in R you just use this package, this soft package. Okay, now I want to show you how to install it. So before you solve the OD, you have to install this soft package. So you go to here, tools, install right package, and then you just type the soft, then select it, and then click install, and to install the server. And actually I already installed this server, so I don't have to install again. But anyway, after you install this server package, you can see you just click the package, and then you can find the dsoft package here. You just click it and to select it in the library. And so before we use it, we had to add this command to add it into the library. Okay, and then you might have a question about what's the difference between this arrow sign and with the equal sign. So typically, right, this arrow sign is similar to equal sign, and you could replace all this arrow sign with equal sign. It won't change the result. And so typically this the approach or the format I use in my program. I will use this arrow sign here, and when we have the parentheses on the right hand side, right? So typically we use the equal sign within the parentheses. Okay. So if we have a equal sign and within the parentheses, I will use the arrow sign here. Alright, just kind of different levels, right? And just made the program look a bit different, right? Between the terms in the parentheses and then outer parentheses. And you might ask me why the parentheses is so important. So for example, so if you define, for example, in this command, we define the parameter value, right? Actually, the acceleration a. So if we use this format, right, and we use equal sign within the parentheses, and then the value of a, the variable of a actually, right, just disappear after we run the program. However, if we put we use this format, we use the arrow sign within the parentheses, and after we run this program, and then we still have the value of a, right? The variable of a still stays in the program. Okay, I will show you later on that. So maybe I'll just show you now. Okay, let me just type in the program. So I'm going to type in the library first. The library. So typically, and you just type in the name. So be careful. So when you type in the package name, and then I'll just automatically show you this available package. Now let me just show you the difference between the arrow and the equal sign within the parentheses. So now let me just show you parameters. So I use the arrow term here, and then I use the equal sign within the parentheses. Right? Okay. So before that, I want to also add this. I also want to add this. These commands here. So the first one is used to close all the previous figures, and the second one is clean up the variables in the workspace, right? So ls, right, the parentheses represent the variables in the workspace, okay? And then rm means remove, all right? So let me remove all the variables in my workspace first, right? And then after that I will show you. Right, I want to remove any a value in the workspace, and before I show you, right? So I just type in graphics off, and then after that I will type in remove, right, list equal to ls. So I just run this tool, right? And then you can see so we should not have any variables in the workspace, right? And then we don't have any figure here, all right? Okay, now let me run the program. So I just run this program first, right? Just run this one, okay? And then you can see let me run this again. So after that, you can see after running the program, you see the parameter here with the value. Okay, now if you want to see the parameter, you just select it and then run it again. So you can see the parameters actually have a equal to this value in the first column. Okay, now how about this? We substitute, replace. So let me just show. If you type a as arrow here, because we don't, again, after we run this program, the variable a just disappears. Okay, now if we change this one equal sign to the arrow side here, and then you run it again, and then after that you could type a. See, so the value of a actually stay. All right, so this is the difference between the equal sign and then the arrow sign. So so typically what I want to say is typically we don't use this, right, arrow sign within the parentheses, okay, right, because we don't want too many variables stay in the workspace, right? Okay, so after this, and then so we could define the value for the parameters, and then we also get initial value for the variable. Here is the distance, and then here this means the sampling time point, right? So for example, we want to record output, right? And so we want to see, hey, at which time points we're going to record data, right? So here we're going to record the data from 0 seconds to 5 seconds, and then the interval is 0.1. So we record all the data from 0 to 5 and with the interval of 0.1. And after that, and then we could use here the ODE, right? The server is come from the package, right? Dissolve, and then we determine the initial value, and then we determine the sampling time, and then we determine the ODE model, and then we determine the parameter values, right? After that, and then after we specify all of these parameters or setting, and then I'm going to solve the ODE and then decode the data, right? So now I want to show you the complete right program. So this one is for the first car, Ferrari car, and then this one we're going to change the acceleration, and then we do a simulation for the regular car. So we have 2 cars. So after that, we plug the first car first, and then again the lines is very important because we want to keep the first profile and at the same time add a second profile, right? And then so here, so the output is recorded in R1 and R2, right? So for car 1 and car 2, so so the output actually is in the format of, right, actually a matrix, okay? And the first column is recorded time, right? Actually the T. The second column recall the distance, which is y. Okay, so we have t and y, right? So therefore, this one is the first column is t, this one is second column is y. So we plot t and y over t. Okay, and this one is the second profile. Okay, so again we're going to get the line with the marker, and then the color for the first one is red, the second one is blue, and then this light width, and this light type one means a solid light, and then so point choice 0 should be square, right, if I remember correctly, and then the point choice 1 represent the circle marker, right? And then for the plot we're going to determine the title as label. Don't forget the unit for the time, and then also the distance, and after that we get the legend. So after that we get a legend here. So this the legend, right, in the location of top left. Again, we don't want the border right along the legend, so the border type is equal to n, means none available. And then we put a legend here, name for the first curve, the name for the second curve, and then again the first color, the first curve had a red color, the second one is the blue color, and also the light types, right, for both of them actually solid lines. So you could use 1, 1, and then this just be consistent, right? So use 0 for the first curve and 1 for the second curve, and then this line width right here. Okay, so typically you will get a curve look like this. A figure look like this. Okay, now I want to show you. Let's type in the program together, right? And okay, so now we already have like the OD model. We also set up the parameters, right? So we just need to set up the initial value. So here is y initial, okay, so 0 again, and then you get simulation time. Actually it's the sample time, sampling time. From is the beginning value, and then 2 is the ending value, and then by is the interval. Okay, and then after that we just type in out 1 ODE server initial value. So I will just initial value times sampling time, and then the function is the ODE model, and then you can get the parameters, right? Okay, after that, and then we do the simulation, right? So we get the result for the first car. Okay, now we're going to do a simulation for the second car. So therefore I copy this one, we change the parameters, right, the acceleration. So you could just put here, maybe you could say again I don't put those annotation comments in the program, right? For example, you could put it here, the car 1, and then you could do this one, car 1. So you put the parameters, and then you want to get, maybe you might put this one below here. Anyway, you can move it around, it doesn't matter, right? Okay, so this, you say car 2, then we get a parameter. Okay, I just delete this one, and then the acceleration for the regular car equal to 4 meter per square second, right? And then I just copy this one, right, and change this to R2. Okay, because we already changed the parameters here, right? Okay, so after that we're gonna plot the data. So we get plot R1 So the first column R1, the second column, so this is Y, T and Y. Then the type here is B, so means we get line and then the symbols, and then we have color, and we get red color for the first curve. Line width equal to 2. Anyway, you could change them, okay? And line type equal to 1 is solid line, and then the marker equal to 0. Okay, should be square. And then again, you could define the title, right? Driving distance, distance, and then you get S label, and then you get time, second, and then you have Y label, and then we get distance, meter, right? So I forgot another place here. So we are done with the plot. Now we just put the lines again. You could just copy all of them. Actually, not necessarily the title and the SY label. Just copy this part, right? But be very careful. You need to change, right? This be R2, and then the time for R2, the Y for R2, and then the color for the second curve is blue, and then the line type is still the same, and then the point choice, actually the marker equal to 1 in the second curve, and then after that we put a legend, the legend, and then the location is top left, and then we get the legend. Alright, the legend equal to A equal to 15.87 square, actually meter per square second, and then the second one is A, right? The acceleration equal to 4 meter per square second, and then we get the border type equal to none, right? And then we get color. So make sure that the color is consistent with the curve, the color you use to get the curve, right? Red and blue. And then I get line type, and for each one's 1 solid line, and then this one, the first curve is 0, the second one is 1, right? Square and circle, and then the line width for both of them, alright, equal to 1 and 1. Okay, so hopefully everything's okay. Let's just run the program. Hopefully we get result. So just Control A to select all of them, and just keep run. Okay, actually, unfortunately, I have errors in my program. So actually, I think I have typo. See, for example, every time when you see the errors, don't feel panic. Just read the comments, right? For example, hey, this is not defined because I have typo here. Change this to change this name back to the T_SIMU. Save it, right? Into S. Select again. Then you run it. So this time I got it, right? You could zoom in. You could get a result here, right? You see the line, right? And the symbol color. Okay, for different cars, you can see Ferrari cars much faster. Okay, and the result actually similar to the one we get from MATLAB. Alright, so you can see the if you want to get a nicer picture, maybe MATLAB is better, right? Because it has better resolution. But you could see, you could in all the good thing is you just type the equation. You don't need to draw the lines. Okay. And then so here just And then again, you could do some practice assignment if you're interested. Okay, so we're done with this video, and I hope you like it.